I'm going to go ahead and get started, but I'll be trying to keep an eye on the chat. And remember, there is a little bit of a delay between when I speak and when you hear me. So be patient and I will get to your question. Okay, let's go ahead and get started. Sorry, I gotta get situated here. All right, so for test 4, you're gonna see some problems like these. You'll notice that in item number 1 from part 1, we have to find an indefinite integral. And remember, integration's the reverse of differentiation. So whatever rules you learned for differentiation, we have to reverse them for integration. So when you look at this problem, what you're hoping is that each term, here's a term and here's a term, things that are separated by plus or minus, will fit a pattern of an integration formula that we know. Because otherwise we have to use a technique like substitution to integrate. So here are some integral formulas, the basic integration formulas. There are books and books full of integration formulas, but these are good ones to know. In particular, items I'd say 1 through 6 and 11 through 16 you should memorize so that you can use them easily when you need them. So looking back at our problem, do we have any of those formulas that have a secant tangent? Let me make this a little bigger. Okay, you see how in the first term we have 7 secant tangent? So we want to know if there's a formula for that. Not the 7, because that coefficient can easily be brought out front of the integral, but the secant tangent part. So if you notice number 13 on the formula list that's posted in your OneNote is integral of secant tangent equals secant. So we do have a formula for that. And then the other one, the other term, had a secant squared in it. And so you want to look at the integration formula and see if we have a secant squared. And, number 11 right above says the integral of secant squared is tangent, which makes sense, right? Because what was the derivative of the tangent that you memorized previously? The derivative of tangent was secant squared. So let's go ahead and use these formulas. And what you see is the 7 stays the same. The integral of secant tangent is secant. And the negative 3 stays the same. And the integral of secant squared is tangent. So you see our solution down here. 7 secant x minus 3 tangent x plus c. Always remember that plus c because what we're trying to actually find is a whole category of functions that would all have this integrand as their derivative. And you can always check your answer on an integral by just taking the derivative and seeing if you get that one back. All right, so I wanted to point out item number 1 because I want you to make sure that you're memorizing the integration formulas. Now you get to take test 4 at home, but not the final, so you need to have those memorized when you go into the proctor lab. Okay, let's look at the next one. Actually, I want to skip down to number 3. All right, so we're trying to find the total area of the shaded region, and we have an interesting shape here. On the left side of the shape, the region is determined. I'm going to split this off here. On the left side, the region is determined by being bounded by the function y equals x on the top and the function y equals x squared over 48 on the bottom. And that goes all the way from the x value 0 to the x value 12. And then from the x value 12 up until the x value 24, we have a different pair of functions bounding the shaded region. On the top, we have the line y equals 12. It's a constant function. And on the bottom, we have the other y equals x squared over 48 again. So whenever you're trying to find the area of a region and it's bounded on the top and bottom by two functions, you're going to integrate from a to b, whatever the bounds are, the top function minus the bottom function with respect to x, or whatever the independent variable is. So notice that in this case, we're going to have to split the problem up, because depending on where we are in the interval, we have two different top functions. So we're going to split this up, and we're going to find an area 1 and an area 2. So area 1 you would find by taking the integral of the top function is just x minus the bottom function, which is x squared over 48. Top minus bottom dx, and that's on the interval from 0 to 12. The second area you're going to find by taking the integral, always smallest to largest, left to right, 12 to 24. And again, top minus bottom. So in this case, it would be 12 minus x squared over 48 dx. Okay, would anyone like to see that worked out, those integrals, or are you okay with me just setting those up? And everyone, please remember to put your name or alias in the chat box so that I know who gets bonus points. Anybody out there? Okay, I think our streaming is still good, so I'm going to keep moving on because I'm not getting a response. So let's go down to this question. So this question asks us to evaluate an indefinite integral. Indefinite integrals are just finding the antiderivative family of functions that have this given derivative, as opposed to definite integrals like we set up for the area problem, where you have values to plug in at the end for your x. So I'd like to go make sure we work at least one of these of this form. So when you have an integral that has a product and maybe even a power, they're of a quantity raised to a power, I should say. Not just a single variable raised to a power like the x squared. We have other operations going on here. We don't have a product rule for integration. We don't have a chain rule for integration. So what we do instead is we use the method of substitution. Now, in this particular question, the instructions are actually very helpful because they're giving you a hint on how to do the substitution. They're saying let u, the variable that we're changing to work with instead of x to make the problem simpler, let u equal x squared plus 13. It's not always the case that we are told what to let u equal. But I can tell you that there are, when you're looking at an integral, there are common things to try letting u equal. And don't be scared to try, because you can try it doesn't work, try letting u equal something else. But in this case, the x squared plus 13, notice, is a quantity that's being raised to a power. That is very often what we let u equal. the quantity raised to the power, raised to a power. Whatever's in the parentheses often is useful to let u equal that. So I'm going to show you how this works in this particular problem, just in case you don't know. And then I'm also going to make you a list of other things you could try letting u equal. So in this case, u is equal to x squared plus 13. Now, what we would like to do is to form an integral that has some kind of equation with expression with u's in it, and then a du on the end. In order to do that, we need to figure out what du actually is equal to. So what that involves is finding the derivative of u, du dx. So the derivative of x squared with respect to u is going to be 2x, and the derivative of 13 is just 0. But when we're finding du, we're not finding du over dx. We're finding the differential du. So you can think of it as just multiplying dx over to the other side. So what we have found is if we let u be defined to be x squared plus 13, that would mean du would have to be 2x dx. And notice that right here and here, we have a 2x dx. I'm actually going to rearrange this integral just to make it clear, because it's very important that when you try to do a u substitution, that your du appears in the integral. So I want you to see that it does. The order in which we multiply real numbers doesn't matter, so this could have been arranged like this. So this part here, the 2x dx, is equal to just du. And then this part here, that is u to the negative 14th power. So we're able to replace all the x's with u's, and all we have to do is to evaluate the integral u to the negative 14 du, which we have a rule for, right? In our integration formulas, we go up to the very top, probably the first rule you learned or second was this one, which is the power rule for integration. It says that to remember, integration is the reverse of differentiation. In differentiation, we move the power out front and subtracted 1 from it. For integration, we're going to add 1 to the exponent and divide by it. So, coming back over here, this is going to be add 1 to negative 14, and you get negative 13. Divide by that, and divide by negative 13, and then we have a plus c. But of course, we're not looking for an expression in terms of u. Our original problem was given to us in terms of x's, so we replace u with what it's equal to, which is x squared plus 13, and that's how they get their answer here. Now, I personally prefer that we not leave negative exponents in our final solution, so I probably would have written it as the opposite of 13 times x squared plus 13 to the 13th power plus c, and that's equivalent. Okay, so that would be how you would work that exercise. All right, so how do you feel about that one? Any questions or concerns? Okay, so I'm just going to make a little list of quantities that when you look at an integral and you realize that it has functions being multiplied or a function raised to a power, and you're not going to be able to use one of our standard integration formulas because it's just too different from it, then if you're going to try to make a u substitution, you're going to have to pick what exactly you're going to let u equal. And with experience, it gets easier. But here, let's go ahead and make a page of possible useful u-substitutions. Okay, so what we're going to do is we're going to say what we're going to try letting u equal. Try letting u equal. Okay, and then we have one of the common ones is the quantity being raised to a power. And by the way, the power might be disguised as a radical. So if it's under the radical, that would be the same thing. Sometimes we let it be the quantity if we have a quotient, because there's no quotient rule for integration either. We would be the quantity in the denominator of the quotient, or of the fraction. And when we have exponentials in our integrals, we often will see that we have a function in the exponent. So it would be the quantity or function in the exponent. Or a lot of times we might need to integrate a trigonometric function, but it doesn't have an x in the argument. It has some complicated argument. So the quantity or function in the argument of a trig function is another common choice for our u-substitution. But that doesn't mean that we always do these things. There's situations where you want to let the entire trig function be the u. So it's just a matter of practice and experience. But here's some of the things that you can let u equal. So I want to go on now to number 8. Okay, which also requires a u-substitution. It's also one of the problems where they actually tell you what the u-substitution is. But in this case, notice that they're telling you to let u be the quantity under the radical. But remember, that's just the same as a quantity being raised to a power. In fact, another way to write this integral would be the integral of 24r to the 7th dr over 6 minus r to the 8th to the 1/2 power. Square root is just a 1/2 power. All right, and well, we'll just worry about that later. So let's go ahead and see how we can do our u-substitution for this one. Again, we're given the clue to let u be 6 minus r to the 8th. So let's go ahead and find our differential du, which just means taking the derivative and slapping a dr on the end there. So the derivative of 6 is 0. The derivative of negative r to the 8th is negative 8r to the 7th. And then we're going to have dr. Okay, so when you look at our integral, you want to be able to identify that we have du up there. Now, the coefficient of the du, the negative 8, is not as important as the variables. The coefficient we can adjust. I'll show you how in a minute, but we can't adjust any x to the 12th or r to the 7th. Whatever there is here in variables, we can't change. So when you're looking to see if you have what you need, you see that you have an r to the 7th dr, so you know you have your du in there. So to adjust this to make it fit the pattern that we want, first of all, remember in your integration formulas, I think it's in here, let me see. Oh, maybe they didn't actually list it in here. So another integration fact that they missed on this one, if you have the integral of k times a function f of x dx, you can always bring that k, if it's a constant, out front of the integral. Or similarly, if you have a k out front, you can bring it in. So we're going to use that idea to make adjustments as we need to. so that our du, negative 8r to the 7th dr, appears inside the integral, and we can make our substitution. So in this, what I always do is whatever coefficient is already there, if it doesn't match up with what I have, I just stick it out front. So that's going to be 24 out front, and then inside we're going to have r to the 7th dr over, and then we have 6 minus r to the 8th to the 1/2. Okay, but what I would like to see there is a negative 8. So I'm going to go ahead and multiply by negative 8 inside the integral. But you can't just multiply by negative 8 because you want to. That changes the value of the expression. So to compensate for that, I'm going to multiply by its reciprocal, negative 1/8 on the outside. So really, negative 1/8 times negative 8 is just 1. So we're really only multiplying by 1. So we haven't changed the value of the integral. So that's a little trick you can do to get your du to match up if it only differs by multiplying by the wrong coefficient. All right, so now let's do our substitution. Out on the outside here, negative 1/8 of 24 is negative 3. And then inside our integral, we have the numerator is just our du. And in the denominator, we have u raised to the 1/2 power. Okay, so we've successfully replaced everything in the integral with u's instead of r's. And now we need to think about how we could integrate this. We don't have a quotient rule, again, for integrals. So that's okay, though. If we just have a single variable raised to a power, it's easy enough to change this to the numerator by writing it with a negative exponent. So we're going to have u to the negative 1/2 du. And now it fits our power rule for integration. So we're going to go ahead and add 1 to the exponent and divide by it. That negative 3, by the way, on the outside of the integral is just going to tag along. At the moment that we apply the integration rule, we no longer write the integral symbol. And we're going to say u to the negative 1/2 plus 1 is positive 1/2 over positive 1/2. And then we're going to say plus c, because this is an indefinite integral. And so this is the function that if we took the derivative, we would get back our original integrand. You probably should go ahead and not leave a fraction in a denominator. And so we're going to remember that dividing by 1/2 is the same as multiplying by 2. And I'm going to go ahead and put my x's back in. So negative 3 times 2 is negative 6. And we have 6 minus r to the 8th to the 1/2 instead of u. Now everything's back in terms of our variable r. And you see this is the answer that we were given here. Okay, so as we're going, please look at each step, make sure that you understand where it came from. And of course, if you don't, just go ahead and type a question about it, or just ask me to re-explain, to walk through the problem again. There's nothing wrong with that. Okay, so you think about if you have any questions for a sec while I look for what we're going to do next. Okay, let's go ahead and do number 9 actually. The reason why I think that would be a good one for us to look at is because on number 9, you have to graph the region yourself. In other words, you're not given a picture of the area. And so when you have to graph a region yourself, that can be a little bit more challenging. So let's take a look at number 9. So for number 9, we have find the area of the region enclosed by the curves x equals 2y squared, x equals 0, and y equals 3. The first thing I want to point out is the x equals 2y squared here. Whenever you have the highest power as a 2, that's going to be a type of parabola. But notice it's the y that's being squared. So normally you probably would very easily graph y equals 2x squared as a parabola opening upwards. In this case, x is the dependent variable of the function and y is the independent variable, and so your parabola is actually going to be opening to the right instead of upward. Okay, and you could just plot a couple of points to figure out where. Some important values are going to be where it crosses the line x equals 0, which is a vertical line, and where it crosses the line y equals 3, which is a horizontal line. So let's go ahead and draw those first. Then we'll figure out where that intersects those lines, and then we'll pretty much be probably ready to go. We might need to plot a couple more points. We'll see. All right, so you get a nice XY coordinate system going here. All right. So x equals 0 is the y-axis. Okay, and y equals 3 is a horizontal line through the y value 3. Doesn't really need to be dotted, but doesn't matter. Okay, and then x equals y squared. Well, where is it going to intersect x equals 0? Well, that would mean that when x is 0, that 0 equals 2y squared, so y would have to be 0 as well. So it goes through the point 0, 0. And where would it intersect the line y equals 3? Well, that would mean x equals 2 times 3 squared, which would mean x is equal to 18. So it's going to intersect out here somewhere, and we'll call that point 18, comma 3. All right, now this particular parabola, the vertex is at 0, 0. And so there would be another point out here at 18, negative 3 if you used symmetry. But in any case, you're going to have a parabola that opens to the right. Okay, and what we're looking for is to shade a region that is enclosed by the 3 graphs. So it has to be enclosed by the 2 lines and the parabola. So a lot of times people actually shade the wrong piece, so be careful about that. We're going to shade this piece right here. It's trapped by all 3, the 2 lines and the parabola. Okay, now the next thing you have to deal with is setting up the integral. And oftentimes when you have x being a function of y, remember this is x equals 2y squared, and this is y equals 3, and this is x equals 0. When you have x given to you as a function of y, sometimes it's easier to integrate with respect to y rather than with respect to x. I'm going to go ahead and set this problem up both ways, just so you can see how it works with a dx and with a dy. Okay. Probably the easiest will be the dy. So remember, definite integrals to find an area are all based on sums of areas of rectangles. So I'm going to draw in this representative rectangle, and the integral, the dy or dx part of the integral is the base of the rectangle. Since this rectangle, The reason I oriented it the way that I did horizontally is so the base, the thickness, the dy, would be facing the y-axis. If I orient it the other way, it's going to be a dx problem. All right, so the dy is the thickness, and we find the area of the rectangle as base times height. So my integral, the dy takes care of the base, but I need to figure out a way of writing the height of the rectangle. Well, in this case, the height is easy. It's just going to be, no matter what random y value we pick here, we could find the height, the x value, by plugging into 2y squared. So for example, if y happened to be 1, then x would be 2, would be the height. Okay, so at any point along this curve, if you plug in a y, a particular y, the x value is 2y squared, and that is the height of your rectangle. So you're going to put in 2y squared. So then you have the height times the base, basically. Now, but what y values do we need to calculate the areas of these rectangles for? Everything from 0 on up to 3 we need to hit. So our bounds on our definite integral would be 0 to 3. So the integral of 2y squared dy from 0 to 3 would give us the area of this curve. Now, another way that a person might work this problem would be to orient the rectangle going the other way. So let's say that we added up rectangles this way. Well, in this case, we would have to use the idea of, to get the height of the rectangle, we would have to take the top function minus the bottom function. The top function being y equals 3, and the bottom function being what? It has to be, in order to do, the thickness here is in terms of x, it's a dx rectangle. So we would need to know for any random x value, what would the height of this rectangle be by plugging into a y equals something formula. Well, that would involve solving this equation for y. So let's do that. So off to the side here we have x equals 2y squared. First I would divide by 2, so we'd have x over 2 equals y squared. Then we would use the square root property, so y would be equal to plus or minus the square root of x over 2. Notice the plus or minus. There's no way to write this as a y equals function without splitting it into two separate parts, the top half of the parabola and the bottom half of the parabola. But we're looking at the top half, the positive y value, so we would just write this as square root of x over 2. All right, so remember that's the bottom of our shaded region, would be the boundary y equals square root of x over 2. So if I wanted to set up and find an integral representing the area in terms of dx, I would have to take y equals 3, the top function, minus y equals the square root of x over 2, the bottom function, in order to get the appropriate height of each rectangle. We would need to integrate that from left to right, x being 0 all the way to x being 18. So these are two different ways that you could set up this problem. Notice that it's much simpler to work it as a dy problem than it is as a dx. And the hint that that's probably going to be the case is that the function was written as x equals 2y squared. It was written as a function of y, so most of the time the dy approach will be easier. Okay. All right, so does anybody have any questions about that one? All right, so if you think of something as I'm talking, feel free to type it into the chat bar. But in the meantime, I'm going to scroll on down to number 13. Sometimes we call these initial value problems. Basically, you're given the derivative and you're asked to find the original function. Now, just being given the derivative isn't enough to know the exact original function, because remember that constant c, we never do know that, unless they give you some more information, and a pair of coordinates will work. So what we want to do is we want to find the function s of t, and we know that s of t is going to be equal to the antiderivative of its own derivative, right? Plus some constant c. And then we'll use this guy to figure out what c is. Except we normally don't, we would just put ds. Okay. All right, so let's go ahead and integrate negative 6 minus 5 cosine of t dt and find out what that original function must have looked like. All right, so this is going to be s equals that. All right, so how do you integrate negative 6? Well, what do you take the derivative of that would give you negative 6? That would just be negative 6t, right? This negative 5, the coefficient of the cosine, is going to stay the same. And we have a formula for the integral of a cosine, right? Remember, the integral of cosine is just sine. So that means that we're just going to write sine of t and then a plus c. So s, or s of t, is equal to negative 6 minus 5 sine of t plus some constant c. So the only extra step over just a regular integration problem would be to figure out what that c is by using the fact that when t is equal to 0, s of t, or s, is equal to 5. So we're going to plug in 0 for t, and we know that we're going to get 5. So that's going to be 5 equals negative 6 times 0 minus 5 times the sine of 0 plus c. Well, negative 6 times 0 is 0. The sine of 0 is 0, so that's going to turn out to be 0. So that means that c is equal to 5. And that's why the answer that we're given is negative 6t minus 5 sine t plus 5. Okay? So when you're given the derivative and a point on the curve, then you can always go back and find the original function. Let me leave that for a minute in case you have any questions. Okay, so if there are no questions, I'm going to move on to item number 16. Evaluate the integral, and we're given the integral of sine 7t plus 5 over cosine squared 7t plus 5. Okay, so there are a couple of different options for working this problem. Clearly, since we don't have a quotient rule, we can't just fit this to a pattern. You can look through the integration formulas, but this definitely doesn't fit any patterns. One option would be to use your knowledge of trig identities and see if you could make it fit a pattern that way. And then another option would be to try using u-substitution. Even if you use a trig identity, you're going to also need to use a u-substitution, but you would use it in a different way. So I'm going to show you the two different ways that a person might work, or two common ways a person might work this problem. Give myself a little more space, but I'm going to write the problem where you can see it, hopefully. Okay, so what we're going to do is I'm going to start with one possibility is, let me rewrite it here real quick. Remember that cosine squared of 7t plus 5 means the same thing as the whole quantity squared. So, so if you realize that you're going to need to use a u-substitution, one possibility is always to let u be the quantity that's raised to the power. So in this case, we would let u be the quantity cosine of 7t plus 5. And then we would find du and see if we have what we need. So du, the differential, is the derivative of cosine of 7t plus 5. The derivatives of cofunctions are negative, so this is going to be negative. Derivative of cosine is sine. And then we have, it's not the cosine of just t, it's the cosine of 7t plus 5. So we have to use a chain rule. So we have negative sine 7t plus 5 times the derivative of 7t plus 5, which is just 7. All right, so in other words, oh, and I forgot my dt here, dt. All right, so that means du is negative 7 sine of 7t plus 5 dt. All right, remember the coefficient of the du is not so important, but we have to make sure we have all this other stuff that's actually represented in the integral, and we do. We have our sine of 7t plus 5. So I'm going to adjust my integral just slightly. Give myself a little room here. I'm going to multiply by negative 7, and that's on the inside of the integral, and then on the outside I'll multiply by its reciprocal, negative 1/7. All right, so if I do that, then I have all of the stuff here, and the dt is my du, and then u is cosine, the cosine part. So let's make the substitution. We'll have negative 1/7 the integral of, and then we're going to have du over, and then this is all going to be u squared. All right, so the question is, was this a useful u substitution? We were able to make the substitution. Does it fit a pattern? Well, it will if we just bring the u to the top. So that's going to be negative 1/7 the integral of u to the negative 2 du. We can use our power rule, so we have negative 1/7. Add 1 to the exponent and divide by it, so it's going to be u to the negative 1 over negative 1. And then we have plus c. Okay, this negative 1/7 divided by negative 1 is just going to be a positive 1/7 plus we can bring the u down to the denominator and make the exponent positive. So 1 over 7u plus c, but we want our t's back. We don't want it in terms of u. So it's going to be 1 over 7 times u, which was the cosine of 7t plus 5. Okay, and then we need a plus c. Can't forget the plus c. All right, which is what my math lab was telling us that the answer should be. All right, so that's one approach to the problem, using a u substitution and letting u be the cosine of 7t plus 5. Let's look at one other way that you might have worked this problem, but you should get the same answer. Okay, so I'm going to copy the problem down again. All right, so we have the integral of, then we have sine of 7t plus 5 over cosine squared of 7t plus 5 dt. Okay, so remember another suggestion that I made on the list of possible u substitutions was that the quantity be whatever argument there is in the trig function. Let's try that option. So in this case, the argument of both of these trig functions is 7t plus 5. So I'm going to try letting u be 7t plus 5. And then that would mean that du would just be 7 dt. We have our dt, of course, but we would need to put in our 7. If we put a 7 on the inside, we need a 1/7 on the outside. And then writing this in terms of u's instead of t's, we would have 1/7 the integral, and we'd have sine of u over cosine squared of u du. Now, this did simplify the integral, but it doesn't quite mean that we could immediately integrate it, that we have an integration formula in that format. You could do yet another u substitution, maybe use a v instead of a u and let v be the cosine of u and go that way, but that's basically what we did in the other problem. What you can do instead, though, is to take a different approach, which is think about if you can use any trig identities to get this to match an integration formula. So I'm going to show you the integration formulas here. Oops. Okay. So the things we have formulas for integrating are things like sine, cosine, tangent, cotangent, secant, cosecant, secant squared, cosecant squared, secant tangent, and cosecant cotangent. Right, so when I was looking at this, I noticed that maybe since I have an extra cosine in the denominator, which is a secant, maybe 1 over the cosine, remember 1 over the cosine of x is equal to the secant of x. So then I thought, well, what could I get secant tangent somehow? So notice that tangent of x is sine of x over cosine of x. And so in fact, if we break this apart, we can break it apart into 1 over the cosine of u times sine of u over cosine of u du. So we do in fact have a secant times a tangent. Okay, so remember that the integration formula for secant tangent, it says the integral of secant times tangent is secant, which makes sense because the derivative of secant is secant tangent. So this is just going to be the secant. Well, I have to carry my 1/7 through, so 1/7 the secant of u plus c. Or since u was 7t plus 5, this would be 1/7 the secant of 7t plus 5 plus c. Now that looks a little bit different than our previous answer. Remember, our previous answer was 1 over 7 cosine 7t plus 5 plus c, but 1 over a cosine is just a secant. So really that's equivalent to the answer we just got. Okay, so either way you work it, you're going to get to the same place eventually. All right, I just want to mention on part 2, if there are no questions, on part 2 of the test review, the quiz. Sorry, I lost my mouse here. Where are you, mouse? There you are. On part 2, number 16, this one matches one of our integration formulas, but it might not be immediately obvious to you that it does. I wanted to point out that if you tried to do a u-substitution for the evaluating this integral, you would have a problem. So if you tried letting u be the quantity under the radical, that would be 144 minus s squared. Then du would be 2s ds. And although we can work with the 2 and we can move that 11 out, replace it with a 2 and put a 1/2 out front, we can't fix the fact that there's no s there. So your du actually doesn't appear in the problem, and that is an issue. So we can't fix that. So you're not going to use a u-substitution for this type of problem. You're going to have to look for one of your integration formulas that match. There's only 2 integration formulas on this list that for types of problems like this. And if you look over here, where was it? Down here at the bottom, this is the one that fits the pattern for number 16. It's you can tell because there's a square root in the denominator. There's no variable except the dx in the top, and it fits a something squared minus x squared pattern. So let's go back over here. All right, so what we're going to use for item number 16 would be the integral of dx over the square root of a squared minus x squared equals, and then you can write it as arc sine or inverse sine, however you want to write it, of x over a plus c. Okay, so to use this formula, you're going to need to figure out what a is. So what is a? What squared is 144? That's 12 squared. So to plug into this form, also you're going to need to bring the 11 out front. So you're going to have 11 times the integral of ds over the square root of 12 squared minus s squared. And now it fits your pattern exactly. But this is a definite integral, so you're then going to evaluate it from 0 to 6 root 3. So this is going to be 11 times, we're going to have the inverse sine of x over a, in this case s over 12, evaluated. We don't put the plus c because it's a definite integral. Evaluated from 0 to 6 times the square root of 3. All right, now whenever you evaluate a definite integral, and we haven't done one yet today, you plug in the top minus the bottom. So what I mean by that is you're going to have 11 times. You're going to plug in the 6 root 3, so you have the inverse sine of 6 root 3 over 12 minus the inverse sine of 0 over 12. Okay? Now, if you reduce 6 root 3 over 12, you get root 3 over 2. So what this is really asking is what angle has a sine of root 3 over 2? Okay, you guys tell me that one. we're almost done today, but if you're still with me, tell me what angle has a sine of root 3 over 2. It's definitely a special angle, right? Would it be the sine of pi over 3 or pi over 6? Any guesses? Okay, if you guessed pi over 3, you're right. 60 degrees has the bigger sine, because this is the way I remember it. 60 degrees, here's the x-axis, here's 30 degrees, here's 60 degrees, pi over 6 and pi over 3. So the sine correlates to the y value, so this one has the bigger y value, root 3 over 2 on the unit circle, and this one has the smaller 1/2. So it's the sine of 60 degrees, so this is going to be pi over 3 minus, now what has a sine of 0 is just 0, right? So you're going to have 11 times pi over 3 minus 0, which turns out to be 11 pi over 3. All right, that's all I wanted to go over today. Unless you have any questions, then we're going to stop here. So does anybody have any questions? All right, well, the term is rapidly coming to an end, so be looking at your deadlines on your tests, setting up your final exam appointment. You can take test 4 at home, but you have to go in to take your final exam. Remember to review and memorize your integration formulas and differentiation formulas, although they are the reverse of each other, generally speaking. So, you know, if you know one, you pretty much know the other. If you have any questions or concerns about grades or particular math questions, you can always send me your questions. So please don't be a stranger, and have a great day, I guess. All right, thanks for attending. Bye-bye.